Okay, let's unpack this. We're constantly hearing that the global energy transition, it really hinges on two things: solar power and battery storage.
Right.
But what happens if the cost of that battery storage, drops so low that it stops being the limiting factor entirely?
Hmm.
Could one specific battery technology fundamentally change the speed and even the security of the entire global energy system?
That is the core question we're tackling today. And it leads us right into this really comprehensive assessment. Sodium ion battery cost projections and their impact on the global energy transition until 2050.
And this isn't just some lab report, right?
No, not at all. This study combines really meticulous bottom-up cost modeling for sodium-ion batteries, or SIBs, with a huge global energy system model. Our
Yeah.
mission today is to see exactly how SIBs could shape the next quarter century.
And the most immediate kind of powerful revelation from this deep dive is right there at the top. The modeling suggests that batteries are no longer projected to be a cost-critical component.
That's the absolute game changer. I mean, historically, battery costs were the choke point.
Always.
Now, this study is projecting that utility-scale battery system capital expenditures, or CapEx, could plummet. We're talking over 80% compared to current costs, reaching these surprisingly low figures by 2050.
That's like what happened with solar panels a decade ago. It just changes the entire planning equation. And it seems like the energy system is just hungry for this.
It is. This modeling projects one of the highest stationary battery demand ever published. It suggests the grid will need somewhere between, 67 and 106 terawatt hours of capacity by 2050.
So the system is just ready to absorb all the cheap storage you can possibly throw at it.
And to understand how SIBs unlock that future, we first need to look at the structural vulnerabilities of our current standard, lithium-ion batteries, LIBs.
Which means we have to talk about critical materials. Lithium, cobalt, nickel, and natural graphite. We know that supply chain is fragile.
It's more than fragile, it's a systemic risk. Take lithium. It's concentrated in a few places like Australia and South America, but then 65% of the refining capacity, it's in China.
And it's the same story with the natural graphite, right?
The same country dominates it. And this creates massive concerns about supply security, about price predictability for any country trying to rapidly build out a clean grid.
So that concentration risk means if geopolitics shifts or if mining can't keep up with EV demand, the whole energy transition could be delayed. Prices could spike.
Exactly. And that is the problem SIBs were specifically designed to solve. They use the most abundant raw material possible for their core chemistry, sodium.
Which is everywhere. It's cheap.
Yeah.
And it's not geographically concentrated.
And it's not just the sodium itself. The whole composition of the electrodes changes. SIB cathodes are typically based on things like Prussian blue analogs or layered metal oxides, and they just substitute sodium for lithium.
Okay, and what about the anodes? That's the graphite problem.
Right. The anodes, which traditionally relied on that critical natural graphite, are replaced by hard carbons in SIBs.
That hard carbon point seems like a huge deal for resilience. We should focus on that.
It is. Because unlike graphite, hard carbons can be produced regionally through a process called pyrolysis, and you can often use biowaste.
You mean like agricultural leftovers or even trash?
Basically, yeah. And this completely bypasses the reliance on imported critical graphite. It drastically improves technology sovereignty and supply chain security.
Okay, but here's where the physical engineering gives SIBs what looks like a permanent cost advantage: the current collector swap. If you build a lithium-ion battery, you have to use expensive, heavy copper for the anode current collector.
And SIBs just eliminate that need. They can use aluminum for the current collectors on both electrodes.
That's both.
Both. And aluminum is cheaper and significantly less dense than copper. It gives SIVs a permanent cost and weight advantage that's just built right into the cell structure.
So if we step back for a second, we have a chemistry that uses abundant non-critical materials. It uses cheaper structural parts. But what about production? Does this mean we have to tear down all those billion-dollar lithium-ion gigafactories?
That's the final and maybe most transformative piece of the puzzle. SIBs are considered a drop-in technology. The operating principles are fundamentally very similar to LIBs,
Meaning what in practice?
meaning the core manufacturing processes, coating the materials, drying, stacking the cells, are largely identical. Manufacturers can transition existing LIB production lines to SIB production with only minor manageable modifications.
Which just drastically accelerates the potential adoption rate. You don't have to invent a whole new manufacturing ecosystem.
Precisely.
This all sounds incredibly optimistic, but every new technology has growing pains. If SIBs are this good on paper and they're manufacturable now, what's the trade-off? There has to be a hidden downside compared to established libs.
That's a critical question, and the current trade-off is primarily energy density. SIBs generally have a lower gravimetric energy density. They're a bit heavier for the same amount of stored energy.
Which makes them less attractive for, say, a high-performance EV or a drone where weight is everything.
Exactly.
But for grid storage, where the battery just sits in a container for 20 years.
Weight doesn't matter nearly as much. And if you look at current competitiveness, SIBs are already at parity. In 2023, the study estimated ETH cells at about 92.9 euros per net kilowatt hour.
And LFP lithium cells were.
93.3 euros. They are already neck and neck, and that's despite libs having decades of manufacturing optimization behind them.
That is the single most important metric. They are starting at parity. So now let's look at where they're going. This study suggests SIBs are on a much steeper cost reduction curve.
That's right. The projections indicate that due to performance improvements in the new active materials, SIBs will show a stronger cost decrease than established LSP libs. They're expected to overtake them in the medium term.
So cost parity is just a momentary milestone. It's not the final destination.
Precisely. By 2035, the modeling shows SIBs becoming the cheaper option. And that's even before you factor in the massive economies of scale that they will certainly achieve.
And the main drivers are still the same. The cheaper cathode material and getting rid of the copper.
Yes, that structural advantage is persistent.
Now, to model how quickly these prices might fall, the researchers use these learning rate, or LR, scenarios. Instead of getting bogged down in the percentages, can you just tell us what these scenarios represent?
Of course. They're essentially modeling three potential futures for global scaling.
Yeah.
The low LR is a scenario where cost development slows down, maybe due to bottlenecks. It's a cautionary tale.
Okay.
The realistic LR is the base case, just steady, predictable cost reduction.
And the high LR.
That's the optimistic breakneck speed scenario. It assumes rapid, widespread, successful deployment that pushes costs down really fast, kind of like we saw with early solar manufacturing.
And they combine those cost paths with market share ideas. Will SIBs dominate, or will they just share the market?
Right. The disruptive innovation scenarios disassume SIBs take 90% of the stationary market by 2050. The shared market scenarios, SMS, assume a 50-50 split.
So when you cross-reference the fastest cost drops with the highest market adoption, you get those astonishingly low CapEx figures we mentioned at the start.
That's how you get there.
Before we dive into the system impact, let's just frame the scale of this. Even with all the focus on utility-scale storage, how big is that market compared to, say, electric vehicles?
It's crucial, but it's still the smaller segment. By 2050, the total global battery capacity for all applications is projected around 357 terawatt-hours. Mobile applications EVs are the giant, with nearly 77% of that total.
And stationary batteries.
They account for a robust but smaller 20.7%, about 74 TW cap. It's a vital market for sure, but mobile applications are what really drive the scale that fuels those lower learning rates.
Okay, now for the part that genuinely challenges our assumptions. We take these projected super cheap, super secure batteries, and we plug them into a global energy model. We assume the system is smart, it optimizes itself for the cheapest, most efficient mix. What happens?
Well, you'd intuitively expect the system to use this cheap storage to unleash a massive wave of solar PV, right?
Absolutely. Cheap storage equals maximum solar. Bank it during the day, use it at night.
And that's the counterintuitive result. The system's overall structure remains largely unaffected. Solar PV capacity is not significantly increased across the scenarios. The variation is minor, only about 4%.
So the model is saying the system had already optimized for solar being the dominant source anyway.
It had.
Then where does the optimization happen if the batteries are suddenly so much cheaper?
It happens in the flexibility mechanisms. And the really surprising result is that wind power capacity actually decreases in all the new scenarios compared to the reference by up to 18% less by 2050.
Whoa, hold on. I have to stop you there. We have massive increases in battery capacity, but we're building less wind power. That completely challenges the idea that you need both wind and solar to cover intermittency.
It does, and here's why. Lower-cost batteries absorb the role of flexibility that was previously provided by more expensive sources like wind, especially for that daily fluctuation. The batteries just become incredibly efficient at shifting solar from midday to evening, covering the daily peak, and that reduces the need for a ton of high-cost wind capacity just to fill those short-term gaps.
So the system is prioritizing the efficient use of the solar it already has rather than just building more solar generation. It's just found a cheaper way to move the energy around the clock.
Exactly. And that adaptation then moves downstream into the industrial processes that convert electricity into other forms of energy, the power-to-X synthesis units.
The plants that turn renewable electricity into hydrogen or synthetic fuels like methanol for shipping or industry.
Yes, the modeling shows that electrolyzer capacities, the units that make the hydrogen, and their operation hours stay pretty similar across the scenarios. The cost optimization shifts to the chemical synthesis units themselves.
Meaning the plants that take the hydrogen and turn it into the final product?
That's right. Because the cheap batteries provide better short-term balancing, the required capacity for those downstream synthesis units can be significantly lowered, and they can be operated less flexibly. For instance, methanol synthesis units could see their capacity decrease by over 25%.
Which makes total economic sense. If batteries are handling the short-term fluctuations, the very expensive chemical plants don't have to be oversized to do the same job. They can run more optimally.
And this brings us to the key adapter in the whole system: hydrogen storage. Low-cost batteries let the system shrink those synthesis units by relying more heavily on large-scale H2 storage for longer duration, seasonal balancing.
So the investment shifts.
The capacity for H2 energy storage becomes highly sensitive to battery costs. It shows these massive swings across the different scenarios. The system effectively shifts infrastructure investment from flexible power generation, like wind, to massive long-duration energy banking, which is hydrogen storage.
Okay, so given all this massive optimization, component reduction, you'd expect huge savings. But now we hit what the study calls the cost paradox.
We do. Despite some scenarios installing 2.4 times more utility-scale batteries than the reference scenario, a huge amount of capital, the total annualized system cost and the levelized cost of final energy, the total cost to you, the consumer, it doesn't differ significantly among any of the scenarios.
That is a staggering conclusion. You install dramatically more infrastructure, you solve the critical material bottleneck, but the final delivered cost of energy stays roughly the same across all these possible futures.
Correct. The energy system is highly optimized, and it converges to virtually the same cost optimum, regardless of the path. Improvements in battery costs lead to a proportional required investment in other supporting technologies, chiefly that expanded H2 storage, and it results in a similar overall system cost.
It's like the price of electrochemical storage is no longer the bottleneck. The system just finds the next most expensive thing it needs to invest in.
That's a good way to put it.
So we circle back to the central finding of this whole study, sodium-ion battery cost projections and their impact on the global energy transition until 2050. The key takeaway seems to be that SIBs, as a drop-in technology with abundant materials, effectively solve the problem of supply shortages or price spikes for storage.
Yes.
They ensure the robustness and security of the transition, not necessarily by making the whole system cheaper, but just by locking in the feasibility of it all.
And that security is the biggest win. It has profound policy implications for things like technology sovereignty. Because SIBs use abundant materials and can be made on existing lines, the study concludes their large-scale adoption doesn't really face any major technical or economic barriers. The system is ready for them.
And that brings us to the final critical insight hidden in this modeling, and it leaves us with a provocative thought for you to consider. This study showed that the timing of battery installation matters a lot.
It does. The scenarios that were modeled with very rapid cost reductions, they actually installed more batteries earlier based on the high demand. But those early, massive purchases created what the researchers called a more costly legacy system.
Meaning they rushed out and bought expensive, less optimized batteries in 2025 or 2030, and that locked in higher costs for decades.
Exactly. In contrast, the scenarios that installed batteries at a more moderate pace, the ones that allowed for future cost improvements to materialize first, they actually achieved a slight long-term cost advantage overall.
So what implications does this finding have for the massive infrastructure decisions being made today, whether it's for pipelines or transmission lines or manufacturing capacity? Is slow and steady really the most cost-efficient path to a fully optimized low-carbon future? Something for you to mull over as you watch the next generation of battery factories come online?